So, under heterocyclic compounds, today let us see the synthesis, physical and chemical properties of oxazole. It's a minor topic to be given by Navanita. So oxazole, ox indicates oxygen atom, AZ indicates nitrogen, OLE indicates that it is a 5-membered heterocyclic ring. So it contains oxygen atom in the position 1, nitrogen in position 3 in a 5-membered heterocyclic system. So oxazole can also be named as 1-oxa 3-azole, 1-oxa 3-azole or 1,3-azole. So the nitrogen atom which is present in oxazole, it behaves as a pyridine type of nitrogen. That means it is a pyridine type of nitrogen is electron withdrawing in nature. Hence, the nitrogen atom which is present in position 3 of the oxazole ring. You can see here oxygen atom in the first position, nitrogen atom in the third position. So 1, 2, 3, 4, 5. So this nitrogen atom, it is electron withdrawing in nature and it behaves as a pyridine type of nitrogen. Therefore, the entire ring will become electron deficient. So this compound was first discovered by Hansch. It has been first known by Hansch as early as 1887, but it was synthesized only in the year 1947 for the first time. So the benzo derivatives of oxazoles are known as benzoxazoles, and they are also having some pharmaceutical activity, and they are also important compounds in the pharmaceutical industry. So this azole, this oxazole, 1,3-azole or oxazole, it does not occur in nature. It is part of very few naturally occurring compounds like alkaloids, but it is very rarely found in nature. So if we consider imidazole and thiazole, they are highly found in the nature. They are naturally occurring compounds, imidazole and thiazole. But this oxazole, it is not a naturally occurring compound. It is rarely found in nature. So if we reduce the double bonds, if you reduce the one of these double bonds in oxazole, we get compounds known as oxazolines. This is a benzo added oxazole which is known as benzoxazole. So the oxazole derivatives possess various types of biological activities such as analgesic, anti-inflammatory, antibacterial and antiviral activities. Similarly, benzoxazoles are also pharmaceutically important compounds. So let us see some of the physical properties now. So this oxazole, it is a liquid. Oxazole is a liquid having a boiling point of 69 degrees centigrade. So oxazole is a liquid having boiling point 69 degrees centigrade, and it has a odor. It is ODOUR, odor resembling that of pyridine. The odor of oxazole resembles that of pyridine because it contains a pyridine type of nitrogen atom. So it is miscible with water and many other organic solvents. And it is a weakly basic compound having a pKa value of 0.8, but it is more basic compared with isoxazole. So when nitrogen atom in the oxazole ring is only in the second position, then it becomes isoxazole. Normally in the oxazole, nitrogen atom is in the third position. When this nitrogen atom happens to be in the second position, the resulting compound is known as isoxazole, so which is less basic compared with the oxazole. So the dipole moment of oxazole is measured to be 1.5 d by units. So oxazole possesses a sextet of 5 electrons. Therefore, it behaves as aromatic compound. So all its properties demonstrate that the delocalization is incomplete. So the reactivity of oxazole shows that the delocalization of 5 electrons is not complete, though oxazole is aromatic in nature. So therefore, there is as a result, it has a little aromatic character. There is a decrease in the aromatic character. Though it is aromatic, there is a decrease in the aromatic character because of the partial delocalization of the 5 electrons. Because of the partial delocalization of the 5 electrons, it is poorly aromatic. There is a decrease in the aromaticity of oxazole. These are some of the physical properties, important physical properties of oxazole. Next, coming to the synthesis. There are 5 different methods of synthesis of oxazole. So the first one is from ethyl alpha hydroxy keto succinate. It is a simple method proposed by Bredrek and Banget. So this is WHICH. So this method involves WHI which. So this method involves a reaction between ethyl alpha hydroxy keto succinate and formamide to give diethyl oxazole 4,5-dicarboxylate, which is subsequently hydrolyzed and decarboxylated to oxazole. So when this ethyl alpha hydroxy keto succinate, when it reacts with formamide, it results in the formation of oxazole ring, which is having this carboxylate substituents. These carboxylates are esters. They are hydrolyzed to carboxylic acids, and then these carboxyl groups are removed as carbon dioxide. So let us see the equations. So this is the equations for this synthesis. So ethyl alpha hydroxy keto succinate reacts with formamide, and on heating it forms oxazole ring with substituents at the 4th and 5th positions. These are ester units. These two are ester units. So it is diethyl oxazole 4,5-dicarboxylate. So these ester functions are reduced to the carboxyl groups by hydrolysis with barium hydroxide. The both ester groups are hydrolyzed to the carboxyl groups, and these on heating with a base like quinoline, the carboxyl groups are removed as carbon dioxide. So 2 molecules of carbon dioxide are removed, resulting in the formation of the oxazole. That is the first method. So this is ethyl alpha hydroxy keto succinate. It is a derivative of succinic acid. So in diethyl succinate, we will have 2 CH2 groups here. In diethyl succinate, CH2, COO, C2H5, COO, C2H5. So this CH2, in place of CH2, we have C double bond O here, and here CHOH. So it becomes alpha hydroxy. So ethyl alpha hydroxy keto succinate. So it is a derivative of succinic acid. So next, coming to the second method. This is Robinson-Gabriel synthesis. So in this synthesis, alpha acyl amino ketones on treatment with an acid catalyst like sulfuric acid or BCl5 undergo cyclodehydration to form oxazole ring. And in this case, we get a tri-substituted oxazole. So we can see the equations here. So this is alpha acyl amino ketone. So this is acyl amino group. Acyl amino. So acyl amino group in the alpha position of the ketone. So So alpha acyl amino ketone, which is having different substituents, when treated with acid catalyst, so it undergo a cyclodehydration. It undergo rearrangement by in a cyclodehydration reaction. So water molecule is removed from alpha acyl amino ketones on treatment with an acid catalyst, resulting in the formation of 2,4,5 trisubstituted oxazole. This is the second method. Let us go to the next method. So oxazole can be prepared from alpha amino carbonyl compounds. So this method consists of refluxing an alpha amino carbonyl compound with an amino ester to give oxazole. So this is amino ester. It contains C double bond NH. This is amino group. So it is reacting with a ketone, amino ketone. This is alpha amino ketone. So the alpha amino ketone will attack the carbon atom of the amino ester, and the resulting compound will undergo rearrangement, resulting in the formation of 2,5-disubstituted oxazole. In this case, we get 5-methyl-2-phenyl oxazole. So these two compounds are refluxed in acetic acid. So the amino ester and alpha amino ketones are refluxed in acetic acid. So it will undergo rearrangement, resulting in the formation of 2,5-disubstituted oxazole. So in the mechanism, amino ester first adds to the carbonyl compound in presence of acetic acid. The ring closure results in the formation of oxazole. The third method. Next, coming to the fourth method, it is from acyl aziridines. So aziridines are three-membered heterocyclic rings containing nitrogen, and in this case, this aziridine is having some substituents. It is having some substituents. So here we have N-tertiary butyl group, and we have benzyl group here, and a phenyl group here on thermolysis. This is a thermolysis reaction, that is heating. So thermolysis of one substituted 3-aryl 3-phenyl aziridine gives rise to 2-aryl 5-phenyl oxazole. So this reaction gives high yields of this disubstituted oxazole. So this reaction is imagined to be proceeding via the azomethane. So then there is a cleavage of the CC bond. So the resulting compound cyclizes to oxazoline. So when heated, so it forms an intermediate. Which undergo rearrangement. So 3-membered ring is converted into a 5-membered ring finally. So it will rearrange to form oxazoline, that is partially reduced oxazole is known as oxazoline. So this on oxidation, that is removal of hydrogen. This on oxidation gives this disubstituted 2,5-disubstituted oxazole in high yields. So thereby aziridines are converted into oxazole. So 3-membered heterocyclic ring is converted into a 5-membered heterocyclic ring by rearrangement on heating. So thus aziridine derivatives, substituted aziridines are converted into substituted oxazoles by thermolysis. Next. So it is also prepared from metallated isocyanides. So isocyanides on treatment with N-butyl lithium forms alpha metallated isocyanides, which on treatment with acid chloride or sometimes on treatment with hydrides are converted into oxazole. So this is isocyanide. On treatment with N-butyl lithium, it forms a lithium salt. So it is lithium isocyanide. This on treatment with acid chloride forms an intermediate which undergo rearrangement. It will undergo rearrangement to form a disubstituted oxazole. That is the fifth method. So from alpha methylated isocyanides, oxazoles can be prepared. These are 5 different methods of synthesis of oxazole. So coming to the reactivity. So it can undergo reactions like the electrophilic substitution reactions and nucleophilic substitution reactions, and there are some reduction reactions which results in the opening of the oxazole ring system, and there is formation of some enoxides. Let us see the reactions with examples one by one. So as I said earlier, this nitrogen atom in the oxazole ring behaves as a pyridine type of nitrogen. That is, it is electron withdrawing in nature. Therefore, substitution of electrophile is somewhat difficult. So under acidic conditions, electrophilic substitutions like nitration, sulfonation and chlorosulfonation do not occur. This is attributed to the highly electron deficient nature of this oxazolium cation. That is, nitrogen is electron withdrawing. Therefore, the entire ring becomes electron deficient. That is, it becomes electropositive. Therefore, substitution of electrophile in the ring is difficult. However, oxazole undergoes bromination and Wills-Mayer-Hack formylation reaction. So let us see some examples here. The disubstituted oxazoles forms some bromo derivatives. So here we can see it is a 1, 2, 3, 4. So it is a 2,4 disubstituted oxazole. When it is treated with bromine or N-bromosuccinamide, it forms a 5-bromo derivative. So when the second and fourth positions have substituents, bromine substitution occurs at the 5th position. And in this example, you can see substituents are present at the 2nd and 5th positions. Therefore, here bromination with bromine results in the formation of 4-bromo derivative. So therefore, bromination occurs by electrophilic substitution either in the 4th position or in the 5th position, depending upon the substituents that are already placed in the oxazole ring system. So formylation. So when treated with POCl3 in DMF, it undergo formylation. So this once again, it is a disubstituted oxazole. On treatment with POCl3 and DMF, it results in the formation of a formyl derivative by Wills-Mayer-Hack reaction. So we get formyl group at the 4th position in this case. So therefore, formylation of oxazole results in the formation of 4-formyl derivative of the oxazole. Next, coming to the nucleophilic substitution reactions. So oxazole undergoes certain nucleophilic substitution reactions on heating with ammonia or formamide. So when substituted oxazole is made to react with ammonia or formamide, so it results in the formation of the imidazole ring system. That is, oxygen atom in the oxazole ring is replaced by the nitrogen atoms that are present in the reagent. So we can see the different steps that are involved in this reaction. The amino group is substituted at the 2nd position. Amino group gets substituted at the 2nd position and the resulting compound undergoes rearrangement. It undergoes rearrangement First it forms a oxazolide, then which undergoes dehydration to form a imidazole. We can see in place of oxygen in the oxazole we have now NH. So oxazole is converted into imidazole. Next, reaction with reducing reagents. So reducing reagents such as lithium aluminum hydride opens this oxazole ring system. So 2,5-diphenyl oxazole is reduced to 2-benzyl amino 1-phenyl ethanol. This is 2-benzyl amino 1-phenyl ethanol on reduction with lithium aluminum hydride. So disubstituted 2,5-disubstituted oxazole, that is 2,5-diphenyl oxazole on treatment with lithium aluminum hydride results in the formation of 2-benzyl amino 1-phenyl ethanol. 2-benzyl amino 1-phenyl ethanol. This is reaction with reducing reagents, and here we can see reaction with oxidizing reagents. So normally this oxazole ring system is stable to the action of hydrogen peroxide, but it has some substituents, then oxidation may occur in the substituted ring system. So for example here it is a 4,2-oxazolyl pyridine. So in pyridine at the 4th position we have the oxazole ring system. So when it is subjected to treatment with hydrogen peroxide and acetic acid, so it undergoes oxidation in the nitrogen atom present in the pyridine ring system, resulting in the formation of an N oxide. So N oxide is formed. So oxidation is occurring in the pyridine ring system, not in the oxazole ring system, because oxazole is normally stable to the action of hydrogen peroxide. So therefore, here N oxide is formed in the pyridine ring rather than the oxazole ring. So this nitrogen also behaves as a pyridine type of nitrogen, but here N oxide formation occurs only in the pyridine ring system, but not in the oxazole ring system. So next, coming to its importance. So it is not a naturally occurring compound. So it is found only in certain alkaloids like pimprinine. It is isolated from Streptomyces pimprina. This is an alkaloid. This is an alkaloid which contains this oxazole ring system. And oxazole derivatives are known to have anti-inflammatory, analgesic, antibacterial and antiviral properties. Is high antiviral properties. So this is a compound. This is an oxazole derivative. So with the substituents in the 2nd, 4th and 5th position that exhibits different biological activities. So 2 amino azoles are used as antihypertensive agents. So the oxazole derivatives possess antibiotic activity. Certain oxazole derivatives are also known to possess the antibiotic activity. So these two are the oxazole derivative. Here we can see the oxazole, benzoxazole ring system. It is a benzoxazole ring system, and here also we can see the oxazole ring system with substituents in the 2nd and in the 4th position. They possess certain antibiotic activities. This is the chemistry, the synthesis, physical, chemical properties and synthesis of oxazole.